All right, so here's my crash course on trigonometry, all right? This covers everything in the unit circle, all right? Not just all trig, but the unit circle specifically, and it covers 4 charts. But before we begin, we have to know a couple of conversions. The first conversion is taking an angular value and converting it to a radian. And what you do is you take the angle, you multiply by pi over 180 degrees, where the degree symbols go away, and you'll get radians. All right, you reduce that to the simplest form to get your radian value. And it should have a pi on it, all right? When you converted something with pi, like a radian or a radian value, you're taking the radians and you're multiplying it by 180 degrees over pi. And the pi should simplify, giving you an angular value, all right? And this is really important when you're working all these charts out, because our charts are dealing with angular values everywhere we go. And we want to consider that the charts we're using here specifically are based on angular values. All right, so let's begin. So when you're dealing with trig and the unit circle, what are the things you need to know? You have 4 charts to memorize. All right, the 4 charts are the quadrant chart, the sine chart, the reference angle chart, and the common angle chart. And the simplest of these 4 charts are going to be this one, the quadrant chart. In the quadrant chart, we have to understand where our angle lies. And to do trigonometry, we're using 3 of these charts specifically to get to our valuation of any trigonometric function. So if we land in the first quadrant, we know the angle must be between 0 and 90 degrees. If we land in the second quadrant, it's between 90 and 180 degrees. If we land in the third quadrant, we're going to have an angle between 180 and 270. And if it's in the fourth quadrant, we'd have an angle between 360 and 270. Now, to get ahead of ourselves, we're going to talk about something called coterminals, which is a hint I provided for another problem ahead. When you're dealing with coterminal angles and you have an angle that's greater than 360 degrees, it spirals past all the values you have here. So it might go around once and twice, right? Like if we add 90 degrees to 360, we'll get this angle again at 90. And so what we do is we'll subtract 360 if the angle is greater than 360. And we're going to continue doing the subtraction until the angle lies between 0 and 360, 0 included, all right? And that's because the 0 angle is the 360 angle. And we'll do the same if the angle is negative. We'll just keep adding 360 until it becomes a positive angle between 0 and 360, where 0 is included in the value. So if it lands on 360, we subtract 360 again, and our coterminal angle would just be 0 degrees. Right? That's really important when we're thinking about the quadrant chart, because if your angle is greater than 360, we'll have to apply this process to find out which quadrant our angle lies in. All right, once we get past this first quadrant chart, which is one of the first defining moments when you're doing trig, we get to the sine chart. And we have this acronym that everybody knows so well, ASTC, in which people say all students take calculus, right? In this case, we're saying when we land in the A quadrant, all trigonometric terms are positive. When we land in the second quadrant over here, since x is negative and y is positive, sine and cosecant are only going to be positive. And we'll get to the reasoning behind this in a second, all right? And when we're in the third quadrant, where we're at t, both terms are negative, x and y. Tangent and cotangent are both positive trigonometric functions. All other functions will be negative in this quadrant. And in the fourth quadrant, cosine and secant are going to be positive, because the x is positive and the y is negative. Now, the big question is, why are these two connected? Well, cosine and secant are inverse functions. And we'll see that later on if we could just pan over to the right. At the right corner, we see the inverse functions, where we have sine is the inverse of cosecant, and cosecant is the inverse of sine. The same as cosine is the inverse of secant. Secant is the inverse of cosine, right? And tangent is the inverse of cotangent, and cotangent is the inverse of tan, right? And so these are really important, and they're the reason why we have this relationship between sine and cosecant, tan and cotangent, cosine and secant. Besides those points, we have to understand the unit circle and how the unit circle forms to each particular angle, wherever the dot may be. If x's and y's are positive, if the x is negative and the y is positive, if the x and the y are negative, or if the x is positive and the y is negative, which puts you in every particular quadrant. So we have a point, right? The point will be the angle. In this quadrant, the x and the y are positive, and the opposite of the angle is going to be your y term. So our sine is the opposite over the hypotenuse, right? And we have this acronym that we always use, which I failed to put up. It's called SOHCAHTOA, right? And this tells us the values of the trigonometric things. But a better way to see this acronym is actually like this. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. All right, and that's where we get these formulas from, because that's where it comes from. The sine is the opposite over the hypotenuse, and the hypotenuse is r in all cases, and we have x as the adjacent side. And also we want to remember that the radius of every unit circle, since the unit circle goes in a circle from 1, 0, 0, 1, negative 1, 0, and 0, negative 1, goes to all these points that go around the unit circle, which is why it's called the unit circle. The radius is also always going to be 1, no matter where it is. What will change is your x and your y value, because every part on the unit circle is not always going to be these 4 points. And that's where the trigonometry really starts kicking in for what we're doing. But if you remember the acronym SOHCAHTOA, sine O over H, C, A over H, T, O over A, based on the acronym, you should be able to guarantee yourself getting this right. And if you could build it off of this, we know that the opposite side of the angle is the y value, the adjacent side of the angle is the x value, and the hypotenuse is always going to be r. So sine here will be opposite over hypotenuse, which is y over r. Cosine will be adjacent over hypotenuse, which is x over r. Tangent will be opposite over adjacent, which is y over x. And that brings us to why these values are positive or negative. So in the second quadrant, sine is, for sine, we have a positive y, right? And the radius is always positive, no matter what, because of this formula, right? So x could be negative, y could be negative or positive, either of them. But the r would always be positive because these will always be positive values when they get squared. So the r is always considered to be a value of 1 and always positive, right? So based on your trigonometric triangles, they might not always have a hypotenuse of 1, but the correlation of triangle that we will compare it to, which we would multiply by a scalar, would be the value of 1. And so cosine has an adjacent with hypotenuse. The adjacent is x. It would be x over r. The tangent would be the y over x because it's opposite over adjacent, and we know the opposite side is y, the adjacent side is x, and the hypotenuse is r. And that concludes how to use the sign chart, right? So remember the acronym, all students take calculus. All are positive, sine and its reciprocal are positive, tangent and its reciprocal are positive, and cosine and its reciprocal are positive. Real basic stuff, all right? Next we have here the reference angle chart. And when we're dealing with the reference angle chart, we have to make sure one thing. We want to make sure to convert our radians to angles before using this chart. It must be an angle when we're using this, okay? Here we have 3 problems I want you guys to try if you have a chance to try it out. But maybe I'll talk about the solution of one of them and the coterminal of the other one so that it leaves you guys something to do while watching this video. So if you're in quadrant 1 and you're between 0 and 90 degrees, you take the angle as it is to get your reference angle. Okay, and the reference angles are really important because our common angle chart has only reference angles on it. However, to determine the sign of your trig function, you need to know the sign chart. To determine the quadrant you're in, to get the sign chart, you need this quadrant chart, which tells you how the angles work. And then to get the reference angle, which we pair with the sign value of it, we'll pair them up together to get these common angles to get a sign on them to determine which quadrant they land in to get the trigonometric function value. So to get those reference angles, again, if you're in the first quadrant, which we talked about back here, you just take the angle you're given. If you're in the second quadrant, you take 180 degrees and subtract that angle. If you're in the third quadrant, you want to take the angle and subtract 180 degrees. And if you're in the fourth quadrant, you take 360 degrees, subtract that angle, and you get your reference angle, all right? And again, if you have angles that are bigger than 360 or smaller than 360, we use the coterminal function to either add till it's between 0 and 360, or we'll subtract till it's between 0 and 360. Okay? So here we have 3 practice problems. The first one says, find your reference angle if your angle is 210 degrees. It would not be fair if I did not attempt this, but if you haven't, if you don't want to see the solution, it's a good time to pause the video and give it a shot based on what I've already said. All right, otherwise, if you're watching it, you did pause it, and you want to see how this works, we'll take the angle since it's 210. 210 lands in which quadrant? We're looking here, we have 180, we have 270, we have quadrant 3 is where 210 is, so it's here somewhere. So we're gonna use this formula. So we have the theta minus 180. Our angle is 210, it lands perfectly, minus 180 degrees. Our reference angle is then 30 degrees, all right? Then I take this 30, I know I'm in which quadrant. Let's say I had sine of 210. Sine of 210, I'm in the third quadrant, right? Sine in the third quadrant, only tangent and cotangent are positive, so all other functions are negative, so sine would be negative. So the sine of 210 degrees, I know already would be a negative value. And the reference angle, so I could put negative sine of the reference angle. And the reference angle again is 30 degrees. So all I really need to know is my common angle value, and I could solve this problem. But so far I took away most of the work of this problem. The last and final step is a chart we can actually memorize, which is right over here. So we'll get back to the sine of 30 degrees in a second. And oh yeah, I failed to mention, I said I would do the coterminal angle of negative 540, right? Because we're gonna keep adding till it becomes a value between 0 and 360 degrees. So we have the value of negative 540. So I'm gonna add 360 to this. Right, if I have a difference of numbers, it's just like subtracting, right? Just the result is gonna be negative instead of positive. 54 minus 36. Right, that's a common thing. I think it's 18, right? They're multiples of 9, right? 9 times 4, 9 times 6, right? So it's gonna be 18 here. So my reference angle is 180 degrees so far, negative. So I'm gonna add 360 again. This is half of this, so it's negative 180, positive 180 now, right? So I have my reference angle here by just adding the coterminal difference, right? To make the coterminal work. And that's all it takes to get the reference angle here. So that one would be done. This would be for part C. If you hadn't already done it, I hope you guys paused before you actually did that one. So then we come over here to the common angle chart. If you want to slide over. And the reference angle chart, I actually completed it. But before we begin, I just want to talk about a few things that we're going to use while we're doing it. Actually, we'll get there when we get there. So to start the first three of these, the first one I'm going to just show you guys. This is the best way to form your own trigonometric table. And you could do this in a test if you had to take a test. It's really easy to memorize how to do this, and there are tricks and patterns to how this whole thing works. And later, when you start applying everything that I had just shown, it all starts to make sense for how the unit circle works. And then you'll have a formal understanding of it if you wanted to elevate your understanding about it. So when we're doing this, I notice I put radians on the first top line. Usually a lot of people like to use angles when they're doing this. So if you could just convert your angle to one of the common angles, or if you're good with radians, I mean, feel free, and nobody's trying to limit or give you a glass ceiling about what you should know. But I think common angles actually works a lot because usually you'll see it in your problems a lot. So 0, pi over 6, pi over 4, pi over 3, pi over 2. The value of pi itself, which is why we use the conversion factor of pi over 180, is pi is 180 degrees. And so if I divide 180 by 6, I get 30 degrees. If I divide 180 by 4, I get 45 degrees. If I get 180 divided by 3, I get 60, and 180 by 2, I have 90 degrees. And that's how easy it is to convert radians to angles. Right? We just use it as a multiplier. That's why we either have pi over 180 or 180 over pi as a conversion factor, depending if we want to go to radians or angles. Once we have that formed out, to get the value of the first line here, the only thing you actually really have to focus on here is the fact that we have the square root of 0, the square root of 1, the square root of 2, the square root of 3, the square root of 4, and this goes up in increasing order from 0 to 4. Each one of these numbers are going to be divided by 2 based on the unit circle when you're using this formula. X squared plus y squared equals r squared, where your r is always 1, all right? And besides the fact of how it's set up, just remember the easy step of 0 to 4, square roots on top, 2 is on the bottom. And once you do this, you can simplify it out to get your results. So the square root of 0 is 0, which means 0 over 2 is 0. Square root of 1 is 1. So square root of 1 over 2 becomes 1/2. This stays the same, radical 2 over 2. Radical 3 over 2 stays the same. There's a square root to 4. So here we get 2 over 2, which is also 1. Now, most of the times people see this and they say, this is a lot of work to generate. Well, I generated these steps because I just wanted to show some square root work in case people need help with other stuff that's before this, but even just rationalizing. But in the real truth of all of this first line is the most difficult line because the second line under it is the same line in reverse order. If you switch this order, you get the value of cosine because they're 90 degrees apart. And so this goes 0, 1/2, radical 2 over 2, radical 3 over 2, and 1. This will go 1, radical 3 over 2, radical 2 over 2, 1 over 2, and 0. The reverse order. And tangent, since over here we see tangent is sine over cosine, right? Or if we really wanted to get technical and look at what like tangent actually was, it's the y over the x, which is the opposite over the adjacent. We see sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So we're just looking at numerators. When we're looking at tangent, we're just taking the numerators of both of these and we're putting them over each other. So 0 over 2 is 0. 1 over radical 3, we rationalize and we get radical 3 over 3. This is also acceptable, all right? Most classes that are just learning this, they don't really care if you simplify the radicands. Some classes do. Ask your teacher about it, you know? Here we have radical 2 over radical 2, which is just 1. Radical 3 over radical 1. Radical 1 becomes 1, so that's just radical 3. Radical 4 over radical 0 is 2 over 0, which is undefined. And we're going to use this term, UND, every time we see this, all right? So the first 3 lines are pretty basic to make. The first line, you make it from 0 to 4, everything over 2. You reverse that order. Then you divide this by this. 0 over 1 is 0. 1/2 divided by radical 3 over 2 gives you this when you rationalize, and so on. If you wanted to make that simpler, just take your numerators and divide your numerators, which is what I just did on this board to show you guys. Now, when we get to cosecant, as we saw over here, cosecant is the inverse of sine. And so sine is the inverse of cosecant. So if we take the fraction we get on sine here, meaning you don't have to do any work to generate this. This is like effortless work. We're taking the 0 over 2 and we're inverting it, right? So this radical 0 over 2 is the first step that I put just in case people had to see the layman term. But realistically, we could take the 0 over 2 or take the 0 and say, when we invert 0, it's undefined. When we invert 1 over 2, we get 2. When we invert radical 2 over 2, we get 2 over radical 2. We rationalize and we get just radical 2. You can see the steps on this. Follow the video. You can zoom in, see what I'm doing. When we invert this, we get 2 over radical 3. We get 2 radical 3s over 3. And finally, when we have 1 and we invert 1, we get 1. Pretty simple. Now, just like sine and cosine are related by flipping, here cosecant and secant are also undergoing the same principle. We just turn this line around. And once we turn it, we see all the work is the same. In any case, secant is the inverse of cosine. We'll take these values and we'll flip them over and we'll put them here. See, radical 4 over 2, 2 over radical 4, radical 3 over 2, 2 over radical 3, radical 2 over 2, 2 over radical 2, and so on. But the easier way to do it is just flip this line around. And finally, if you thought there were no more tricks left in flipping and stuff, when you look at cotangent and tangent here, you'll notice that these 2 lines are also turned around. And the reason for it is because they're inverses of each other also. You see, tangent is the inverse of cotan, and cotan is the inverse of tan. And so what happens is when we just turn this line around, we finish the entire trigonometric table, and all you're really doing is the first line, the second line, the third line, and using small tricks to complete the end of it, all right? And that's all there is to it.